In the chart that I've given you in this particular lesson, I have a listing of things here. One of the things that you need to look up is the mass of the lithium-6 isotope atom in that chart, and you find that it is 6.01512 AMUs. Now remember, AMUs is atomic mass units. That's the average number of protons and neutrons in that particular isotope. All right, we have 3 protons. So 3 protons is 3 times 1.00728 AMUs. 3 neutrons is 3 times 1.008665 AMUs. So we take this quantity and subtract this and subtract this, and we get negative 0.229275 AMUs. Now you notice I'm not really adhering to the significant figure rule that I've always used because we're dealing with such small quantities. We're trying to keep an account as much as we can, and then we'll do some rounding off later on. So this is what we call the mass effect. That means we have lost this many AMUs when we went from the 2 types of particles, protons and neutrons. They are individually have so much of a mass, and then they're all put together and bound together within the nucleus. Then we have that many AMUs of mass that's been converted into energy. So the mass effect is we've lost this to create the energy to hold these particles together. Remember, in a nucleus, protons don't like being near each other because they're all positively charged. The neutrons are there to kind of buffer the repulsion and keep them all together, and the energy then is brought in to bind all that together, keep it from flying apart. Otherwise we wouldn't exist. Now the second part of the problem that we're trying to find is the binding energy. How much energy are we talking about? So this is where the E equals mc squared comes into play. Okay? Now, we need to convert the mass into kilograms because, as we said, this is joules, this has to be kilograms. But we are given here AMUs. So we're going to look at the mass, and we're going to take a negative 229.275 EMUs, or AMUs. Now I'm doing a commercial for Liberty Mutual. And this represents 1 atom. But as we know, 1 mole equals 6.02 times 10 to the 23rd atoms. Okay, so that being the case, then I'm going to take the AMUs and I'm going to change, since that's equal to 1 atom, then I'm going to have negative 0.22975 grams per 1 mole. Since that's what that is telling us right there, then I'm going to take 1 mole is equivalent to 6.02 times 10 to the 23rd atoms. And then I'm going to change my grams to kilograms. Grams here, kilograms here. 1 kilogram is equal to 1,000 grams. And when the smoke clears, I get negative 3.81 times 10 to the negative 28 kilograms. At this point now we are rounding off because now we're getting to larger, more identifiable units that we are going to deal with. So I'm going back to 3 sig fig rules I try to keep. Now we can use this in our equation E equals mc squared. The mass effect is negative 3.81 times 10 to the negative 28 kilograms times, and then c squared we said is 9 times 10 to the 16th meters squared per second squared. And we get a value of negative 3.43 times 10 to the negative 11th joules. Now this is an incredibly small quantity of energy only because we're dealing with 1 mole, or 1 atom rather, of mass, 1 atom of mass. So when we get to energy this low, joules kind of, if we were to change this over to per mole, we would multiply this by that, get rid of that 6.02 times 10 to the 23rd we divided by, and we're going to get an answer of 2 times 10 to the 13th joules, which is 20 trillion joules per 1 mole of this substance, which is a tremendous amount of heat, which is why we like nuclear energy. But what we're looking at instead is just in 1 atom, and so we use something called an electron volt. And when we get into physics, we get into this a lot more heavily, but suffice it to say that 1 electron volt is equal to 1.60 times 10 to the 19th joules. So if I want to look at how many electron volts, which is a measurement of small packets of energy, then I'm going to take that negative 3.43 times 10 to the negative 11th joules and multiply by 1 electron volt over 1.60 times 10 to the 19th joules. And I will get an answer of 2.14 times 10 to the 8th electron volts. Now, if I want to use my SI conversion method for using labels that more adequately represent this, we can change this to mega electron volts because mega means million. So I'll multiply this by 1 mega electron volt over 10 to the 8th electron volts. 10 to the 6th 6 electron volts. Mega means million. And that's going to give us 214 mega electron volts. And in this area of nanophysics and nanochemistry, we use the most, shall we say, the highest level of units involved in this for prefixes. So we use mega electron volts. But this is just for 1 atom. This is just a tremendous amount of energy. Now, in the nuclear plant that we have up in Cordova, that is what we call a fission reaction. In a fission reaction, we take uranium and we bombard it with neutrons, and the neutrons then split the atom down into different parts, and then more neutrons are created. We get this chain reaction taking place, and you get an amazing amount of energy being created from a very small mass compared to what we burn with coal. And like I said, the byproducts, while are toxic, don't go into the atmosphere unless something horrible has happened, like it's happened at 3 Mile Island in Pennsylvania or in Chernobyl in Ukraine. Then ideally, the best heating system, energy creating system, is the fusion reaction, and there's a lot of research going on there, and there's some really interesting ideas coming forth, and that may be the wave of the future. And that is the opposite of fission. Fission is splitting apart of an atom. Fusion is the bringing together of an atom. All stars are gigantic fusion machines, and the amount of heat, as you know, comes off. It's so great that it warms our planet, and we're like 93 million miles away, we still feel the effects of this amazing amount of energy being given off. If we can just harness even a small part of that, we could solve so many problems with that, and that is the goal of science right now, is in a lot of aspects of science is getting that done. So, just a little few things I threw in there, that's all in the script. You have 3 practice problems for that. Use the chart that accompanies the lesson for those 3 problems. Have fun.